In today's video, we'll be discussing physical chemistry one-stop physical revision. So, first chapter is mole concept. Mole concept, we have law of constant composition or definite proportions. Elements are always combined in same proportions by mass. Example is H2O contains a fixed amount of percentage H and O. Multiple proportions, two elements more than one compound have different masses of one element that combine with the same mass of another element are the ratio of small numbers. For example, 12 gram of carbon and 32 gram of O2 combine in 12 is to 32 ratio. Same, like it's kind of common sense, for CO2 I'm talking about. Then reciprocal proportions, when two elements combine separately with a fixed mass of a third elements, then the ratio of their masses in which they do so is same or the multiple of that. So example would be this. CH4 has like 12 gram C and 4 gram H, and this one has 12 and 32. So basically we can say that um, this is what the law states, that the ratio of carbon to oxygen, which makes up the other element in both the molecules, should be 3 is to 8 or a multiple of that ratio. Okay. Then 1 gram atoms is 1 mole of atoms, which is equal to Avogadro number of atoms. Gram atomic mass is mass of Avogadro number of atoms. Now, average atomic mass is very important. It is A1x1 plus A2x2 divided by x1 plus x2 plus x3, where A1, A2 is isotopic mass and x1, x2 is natural abundance of isotope. Mean molar mass or average molar mass is M1, N1 plus M2, N2 plus N3, N3 divided by N1 plus N2 plus N3, where M1 and M2 is molar mass and N1 and N2 is number of moles. Specific gravity is density of any substance divided by density of water at 4 degrees Celsius. Vapor density, everyone thinks it's molar mass divided by 2, but not always. Density of vapor at some temperature and pressure divided by density of H2 at that constant temperature and pressure at that temperature. Okay, basically. Then percentage yield is actual yield by theoretical yield into 100. Okay, so now we have concentration terms for homogeneous solutions or mixtures. We have percentage W by W, which is X gram of solute in 100 gram solution. And now X percentage W by V is X gram of solute in 100 ml solution, and X ml solution is in 100 ml solution. For gases, percentage by volume is also equal to mole percentage, which is number of moles by total number of moles into 100. Okay, then you have parts per million. I'm skipping molality because I'm pretty sure everybody knows that. Mass of solute divided by mass of solvent into 10 power 6, uh, or mass of solute divided by mass of solution into 10 power 6 is your parts per million. Volume strength is equal to molarity. Volume strength, molarity is equal to molarity times 11.2 is equal to volume strength. Then we have two examples. 9 moles of D and 14 moles of E are allowed to react in a closed. Calculate number of moles of B in the end of the reaction. 4 moles of G are present in reaction vessel. So first limiting reagent निकालना है. So we will divide 3 sorry we will divide 9 by 3, and we check if it's greater than 14 by 4, because coefficient given number of moles divided by stoichiometric ratio. So from that you will get limiting reagent is equal to D. So 9 moles of D reacts to 12 moles of E to give 80% of 15 mole of C. 15 mole of C because overall there are 3 moles, right? Because like overall there are 9 moles of D. So, and they are combining in these ratios. So 80% of 15 mole of C will be formed, which is 12. Okay, 12. So limiting reagent of the second reaction is G, because G you will get the ratio to be as 12 by 3. And what is this, 1 second, G, 4 moles of G, right? So 4 by 5. So obviously 4 by 5 is the lesser combination, right? So from there we can conclude that limiting reagent is G. So 5 moles of G gives 6 mole of B. 4 moles of G gives how many? We are taking 4 moles of G because that's what they are given. So then you'll get 4.8 is the answer, but percentage yield of this reaction is 50%, so 2.4 is the answer. Then we have 11.6 grams of organic compound having formula CnH2n plus 2 is burnt in excess O2, 22.4 liter vessel. Before reaction, gaseous mixture is at 273 degrees, pressure reading 2 atm. After complete combustion, mixture of product and excess of O2 has 546 and 4.6 atm pressure. So we have initial pressure. Initial data is pressure, volume, temperature. Then you can use PV equals nRT and get number of moles, initial number of moles of your CnH2n plus 2 and your O2. Okay. Then finally we have these data that will give us the number of moles, and this is the number of moles of excess O2 and mixture of product, meaning NCO2 N plus 1 H2. Now we have initial number of moles, final number of moles, and everything is in terms of N. So we can take that moles of fuel burnt is equal to X. Basically it's 11.6 divided by mole. That's the number of moles of fuel burnt. So we are considering that is only the limiting reagent. So let hydrocarbon be X. Um, and O2 will be 2 minus X because initial number of moles is 2. So final moles, see, initial number of O2 is 2 minus X. So there is some O2 that is left out. So 2 minus X minus 3N plus 1 into X divided by 2, because that's how many moles have been consumed in the reaction. As you can see, the stoichiometric coefficient of O2 is 3N plus 1 by 2 O2. So there have been that many O2s that is used up. So initially there were 2 minus X, and now 3N plus 1 by 2 is used up. And then finally we have NCO2 and N plus 1 CO2, but times X, because we have to take stoichiometric ratio times the number of moles that have been reacted. So for this you can equate it to 2.3, and we have only N in terms of the variables, because here also you can substitute X is equal to N and get the answer. Then atomic structure chapter, isotope, number of protons same, isobars, number of mass number same, isotone same number of neutrons, isoelectronics same electrons, isostar same number of atoms and electrons, isodiaper is A minus 2Z is same. Okay, then we have this relation. I mean, mass number is equal to Z plus number of neutrons. Rn is equal to R naught into A power 1 by 3. Distance of closest approach is equal to half mv alpha square is equal to k q1 q2 by r square. That also everybody knows. This formula everybody knows. Bohr's quantization is equal to mvr is equal to nh by 2 pi, and resultant centripetal force is mv square by r. Remember to just equate them. En is equal to 2 pi square m e power 4 k square by n square h square. Obviously En is directly proportional to q square and directly proportional to k square. You can remember the formula like this, or whatever question comes you can solve. Then En is equal to z square by n square and 13.6. This and all everybody knows. These two constant I think everybody knows. 2.18 into 10 power 6 for velocity. R is equal to 0.529. This is okay. Then ionization energy is equal to E at infinity minus E at ground state. Okay, that is a very important formula. And then we can look at PE is equal to minus 2 ke. Spectral lines, longest wavelength line or shortest lambda line is H alpha line, which is the first transition line. Okay, then NC2 is the formula for what do you say, energy level N to ground state. Delta N into delta N plus 1 by 2 is N2 to N1 transition number of spectral line in atomic samples. N2 minus N1 is number of spectral line in isolated atoms. Okay. Then you have Lyman is UV, Balmer is visible, and Passion to P fund. It is in infrared. I'm pretty sure you guys know the order. A photoelectric effect, effect of intensity and temperature. If intensity increases, then current also increases. Then temperature increases, there is no effect on this reaction. Rest all is common sense. Right, so we can see that it is grounded. The plate is being grounded so that this plate can be kept neutral. Okay. De Broglie wavelength h by mv h by p. All material particles shows wave and particular nature. 2 pi rn is equal to n lambda. Number of waves is also is equal to n in this, which is equal to principal quantum number. 150 by volt v in volts in is the de Broglie wavelength in a angstrom. Then delta x into delta p is equal to h by 4 pi. Short trick is delta h by 4 pi is equal to to 5.27 into 10 power minus 35. 5.97 into 10 power minus 5 is when you divide it by mass of an electron. Quantum number is very direct. We can look at size of orbital, L is shape, M is orientation, and number of angular loads is n, number of radial nodes n minus L minus 1, number of nodes is n minus 1, orbital angular momentum, spin angular momentum, we guys know. Thermodynamics, we have intensive property, do not depend on the do not depend on the amount of matter. Example is pressure, temperature, etc. Extensive property depends on the amount of matter. Example, mass, volume, heat, capacity. All process equations are common sense. We all know that isobaric, isochoric, all that. So internal energy is sum of all the energies like rotation, bonding, translational. The state function, it's a state function and it is extensive. Kirchhoff law of equation of changing delta H with respect to T. This is a very important formula, is being used in N Avasti level 2 and can come in J means. So delta H T2 minus delta H T1 is equal to NCP delta T. Okay. Same thing you can do for delta U with CV. Zeroth and of first law of thermodynamics everybody knows. Then you have this equation of first law of thermodynamics, U is equal to Q plus W. When Q is entering the system, it is positive. When Q is exiting the system, it is negative. When work is done on the system, it is positive. And when work is taken out of the system, it is negative. Okay, so remaining thermodynamics, work done in adiabatic process. Work done in adiabatic process is defined as um delta U is equal to a W. Basically, this is okay. We know this equations. We know this equation actually. P2 V2 minus P1 V1 divided by gamma minus 1, or actually it should be 1 minus gamma, but it doesn't matter. Then you can also look at NR delta T by 1 minus gamma, like that. Also you can look at it like that. And if process is irreversible, then you can consider that it is T2 minus T1 by gamma minus 1 is equal to P external into T2 by P2 minus T1 by P1. Then we can look at the cyclic process. Clockwise area is negative and anti-clockwise area is positive. Okay. Then heat capacity, you have Cp is equal to delta H by delta T in constant pressure. Cv is equal to delta U by delta T in constant volume. So basically from here we can conclude that C is equal to dq by dt. Correct. So gamma mix is equal to N1 Cp1 plus N2 Cp2 and so on, divided by N1 Cv1 plus N2 Cv2 and so on. C of a polytropic process is molar heat capacity is equal to Cvm plus 1 R by 1 minus X, where X is the polytropic constant, PV power X, right? So as second law of thermodynamics talks about the efficiency of the engines. Delta S system plus delta S surrounding is equal to 0 for reversible process. Delta S system plus delta S surrounding is greater than 0 for irreversible process. Carnot efficiency is 1 minus T1 by T2 or 1 minus Q1 by Q2. Okay. We can also talk about the efficiency is equal to the work input divided by Q. So let me continue from where I left off, which was heat. No, I think I did till Carnot efficiency. Or did I? I don't know. Yeah, I think I did till here. So efficiency is also work input per Q. Entropy is defined as dq ref by T, cyclic integral, T1 to T2. You basically are integrating this, and you'll get delta S equation as NCV ln T2 by T1 plus NR ln V2 by V1, which is also equal to NCP ln T2 by T1 plus NR ln P2 by P1. Okay. Then variation of delta S with temperature and pressure. We have Kirchhoff's equation delta S T2 minus delta R S T1 is equal to this shit, right? And then that's all. And then you have delta G is equal to H minus Ts, delta G is equal to delta G naught plus RTL and Q. Van 't Hoff's equation you have this equation. Thermochemistry, delta HF of C graphite is 0, delta HF of S rhombic is 0. Enthalpy of neutralization, strong acid plus strong base gives salt plus water. Delta H of neutralization is minus 56. Resonance enthalpy is delta H of experimental minus delta H of calculated, or delta HC calculated minus delta HC experimental, where F is formation, C is combustion. Then we have bomb calorimeter question. Stearic acid is a fatty acid with part is okay. Basically, it doesn't matter about the mass of stearic acid, how much we take. We can start directly by saying Q released is equal to Q of bomb calorimeter plus Q of water. Then you just use MS delta T to find Q of water, and you use C delta T to find the Q of calorimeter, and then you get your answer. Okay, then we have efficiency cycle of this, what do you say, the process of this cyclic process. So A to B, we analyze that delta U is 0 because temperature is constant, work done is negative, and Q is positive. So from here we can conclude that Q is equal to 2 nr T naught ln 2 because of this value. B to C, Q is taken from the system because the temperature is reducing from 2 T naught to T naught, and the work done in this process is P into minus P into V naught minus 2 V naught, where pressure is equal to nr T naught by V naught. Okay, then you have C to A process where Q is given to the system. Q is given to the system like this. Delta U is equal to Q, nr T naught is the value of the Q, and now we have total work done. Process AB to process BC. We have to take the what do you say, heat absorb, basically heat absorbed in process CA and process AB, but work is only done in BC and AB. So then we write the work done divided by the heat absorbed, and then we get the answer. All right, then you have chemical equilibrium. Kp is equal to atm power delta Ng, Kc is equal to molarity power delta Ng, Kp is equal to Kc into RT power delta Ng, Kp is equal to Kx into P power delta Ng. If reaction is halved, equilibrium constant is equal to square root of original equilibrium constant. Add two equations, multiply equilibrium constant, reverse the equation, it becomes 1 by K. Degree of dissociation and vapor density. Degree of dissociation is equal to D, capital D minus small d by small d into n minus 1, where D, capital D is theoretical VD, small d is observed VD, n is number of moles of products, and formed by 1 mole of reactants. Okay, Le Chatelier principle, we have effect of change in pressure on melting point. So first, if there are two cases over here: solid which contract on melting, such as diamond, ice, magnesium nitride. Solid, if the higher volume, becomes liquid of the lower volume. If pressure is increased, then the reaction moves towards lower volume side. Melting point is lowered. Okay, opposite for solids which expand on melting. Okay, basically if pressure is increased, then volume has to decrease. So where is volume lesser? In the liquid phase, so the equilibrium will move on the right side. Solubility of substance depends on exothermic or endothermic process of solubility. Solubility of gases in liquid decreases in volume, increases in, like, basically solubility of gases in liquid causes decrease of volume. So therefore we increase the pressure and it can favor the reaction. So basically, when you dissolve a gas in the when you dissolve a gas in a liquid, your volume will decrease, so your increase in pressure will favor that. Inert gas addition, when product moles and reactant moles are same, there is no change. When product moles and reactant moles are not equal, then we can say that um what do you say, the constant volume, if you add the inert gas in constant volume, it won't change anything. If you add the inert gas in constant pressure, it will move towards the more mole side. Now we have this equation, which is your Haber's process: high temperature, removal of NH3, addition of inert gas at constant pressure, and low pressure. Actually, I think low pressure is favored for this process. I mean, low relative pressure is actually, like, I think 200 to 900 atms. So something around that much. But yeah, basically, yeah. Then we got ionic, which is basically, I'm assuming that you guys know the basics. So apart from that, pH is decreasing when temperature increases. When two weak acids are present, delta, I mean H H plus concentration is Ka1C1 plus Ka2C2. OH minus concentration is Kb1C1 plus Kb2C2 if these are two weak bases and are present in the same solution. Then you have salt hydrolysis. Salt hydrolysis, interaction of cation with anion both with H2. An example is given over here. So we can say that NH4Cl is an acidic salt with H2O, it reacts to form NH3 and H plus. Then you can assume this is C, this is C minus CH, this is CH, CH, and H is a degree of hydrolysis. Then CH squared by 1 minus H is equal to KH. So KH is equal to, we can say that KH is equal to KW by Ka, like that we can say it to be. And then if H is less than 1, we can also approximate and do our shenanigans over here. So like that we can derive these formulas. So SA strong acid weak base is an acidic salt, and we can use pH is equal to 7 minus half into pKb plus log C. Strong base weak acid basic medium, it's a basic, so pH is equal to 7 plus half into pK plus log C. Weak acid weak base, it can be either acidic or basic depending on pKb values, and pH is equal to 7 plus half into pK minus pKb. Amphiprotic, basically you can have pH is equal to pK1 plus pK2 by 2, and it's valid for amphiprotic salts such as HS minus, HCO3 minus, right? So now we have buffer solutions, acidic buffer, weak acid, strong base, conjugate base. Basically weak acid and its conjugate base, because weak acids have strong conjugate bases. So same way you can say for CH3COH and CH3CO minus, NH3PO4 and H2PO4, H3PO4 and H2PO4 minus. Then we can talk about basic buffer solution, which is a weak base with the conjugate acid, and an example is given here. Henderson equation everybody knows. Midpoint of titration is pH is equal to pK. Buffer capacity is number of moles of acid added per liter divided by change in pH. Indicators, we can say that it is a pH is equal to pK plus log of IN minus by HIN. Detectable color change is when pH is equal to pK plus minus 1. We have methyl orange, which is red, which turns red in acidic medium and yellow in basic medium. Methyl red turns red in acidic medium and yellow in basic medium. Phenolphthalein turns colorless and pink, colorless in acid medium and pink in basic medium. In strong acid strong base titration, we can use any indicators. In weak acid strong base titrations, we can use phenolphthalein. In strong acid weak base titrations, we can use the methyl red or methyl orange. In weak acid weak base, you cannot use any indicators. So then we have solubility, which is kind of common sense. Q is greater than KSP, it will precipitate. Q is less than KSP, there is absolutely no precipitate, and rest all of solubility is easy like common ions. I'm assuming that NCRT some points are given over here, like if K is greater than 10 power 3, products are dominated, and in reaction of Fe3 plus SCN gives FeSCN2 plus. If you add Hg2 plus ions, the red color disappears, and if you add a potassium thiocyanate, it increases the equilibrium and becomes more red and more intensity of red color, because of basically the HC's formation of HgSCN4, which is a very stable compound. And one more is there, effect of temperature can be seen in an exothermic reaction. So we can endothermic reaction. In room temperature, it is blue in color because of COCl4 formation, pink in color because of when you freeze the mixture and it become into a this thing COH2O6, like that. So we'll be discussing this example question, which is very easy actually. Like, don't need to be scared of looking at it. A solution of weak acid HA is titrated with base NaOH. The equivalent point is reached when 40 ml of NaOH is of 0.1 NaOH has been added. Now 20 ml of 0.1 HCl were added to titrated solution. pH is found to be 5. What is the pH of 20 0.2 NaOH and 20 or 0.2 HA? So we can say that HA plus NaOH gives Na plus H2O. So 40 ml of 0.1 NaOH gives 4 ml of 4 millimole of NaOH. So 4 millimole of NaA is present in the solution. Okay. So from here we can conclude that 4 millimoles of Na, and they have given how many? 2 millimoles of HCl. So effectively 2 millimoles of HA will be formed, and 2 millimoles of Na is left. So it is a buffer solution, right? Because you have conjugate this thing, base and an acid. So from here you can apply your Henderson equation and get pK is equal to 5. From here, you can read the second part of the question, which says you have to find the pH of this solution. So from here, you can just apply the pHs, like you can react these two. They'll obviously give 4 millimoles of any. This is supposed to be 4. All right, let me change it. This is supposed to be 4 because they have given 0.2 millimoles and 20 ml. So 0.2 into 20, which is equal to 4. So that's why 4 millimoles of each will be added, and then you will get 4 millimoles of NaA. Concentration though you can find out because there is 20 ml of solution, 20 ml of solution, total volume is 40 ml. So the concentration will be equal to 0.1, and then you can put your hydrolysis formula because NaA plus H2O is formed. Then you can put your hydrolysis formula and get the answer as 9. That's how you do this question. Next chapter we'll be discussing is redox reaction. Majorly in this portion, I'll be discussing the what do you say the titrimetric type questions. Like I'll be taking up 3-4 titrimetry questions or titration questions, and apart from that, we have one formula which is this, and we can find out the n factor of disproportionation, like equivalent weight, right? So to find the equivalent weight, we can use the n factor of disproportionation reactions, where n1 is the oxidation change state of one, and n2 is the oxidation state change of the other one. Like for example, H3PO2, if it disproportionates into pH3 and H3PO3, this we know it's a known reaction of P block. This one and this one have different oxidation state changes. We can just plug it in this formula and get the answer. Like that also, some common n factors we have to know. Like it will be easy if you mark this up easily, or if you just remember them. Like for example, this reaction, right? As2S3, this shit with NO. I think it's ASO4 2 minus. Basically, but basically this change, something like this. I think this change n factor is 28. You have to just remember. Okay, n factor is equal to 28. So like that, I mean, obviously you can balance it. I'm not saying that you can't or you can't check. Like it'll be easy as hell if you just directly know that this is 28. I mean, it's convenient. So we have this question which was asked in NT Abhyas and also then NOSC. So to a 10 ml 1 molar solution of aqueous Br2, excess NaOH is added so that all of the Br2 disproportionates to Br and BrO3 minus. Resulting solution is made free of Br minus by excess of OH, and excess of OH is neutralized by acidifying the solution. The resulting solution is sufficient to react with 2G impure CaC2 whatever is which of the following is the correct percentage purity. We have to find percentage purity of the sample, oxalate sample. Okay. Here I'll be balancing the equation first. So first we have one electron exchange over here, correct? So I mean, so first step is we have to write the equations like this. So the balancing method is first you put what do you say your two electron. So you write the equation separately. Br2 gives 2 Br minus. There's two electrons exchange here because each Br is going to minus. So we multiply this equation by 5. Then second equation we write it as Br2 and 2 BrO3 minus. And here each Br is converting into 5. Okay. 5 electrons are exchanging in each Br. So totally 10 electrons have been exchanged. This you don't multiply by 2. Sorry, by mistakes I've written. And this will be 10 electrons. All right. This will be 10. So then you add them and then you get this equation which you can entirely divide by 2. So finally you get 3 Br2 gives 5 Br minus plus BrO3 minus. So from here the given data is that everything is made free except for your BrO3. They have only said that everything is made free except BrO3. So we know that BrO3 will react. So 3 mole of Br2 produces 1 mole of BrO3 and they have given how many? 10 millimoles, right? 10 millimoles. We can just also write this as millimoles because I don't want any shenanigans, so we'll write this as millimoles. And then you can get 10 millimoles of Br2 will give X of BrO3. So from here we can get X is equal to 10 by 3. So 10 by 3 millimoles of BrO3 minus acts with 2 gram of impure CaC2O3. So basically molar mass is also given. From here we can calculate that the Number of moles is 1 by 64. So like that we can get. But actually, wait 1 second. I think I did a mistake. But 2 gram of impure CH2O3. So we have to take mass of CaC2O3 divided by 128 is equal to 10 by 3. Like that, I think. So from here we can easily get the mass of it. And obviously this is in millimoles, right? So we multiply with 10 power minus 3. From here you can get the mass and you can get the percentage purity. So from here whatever mass you get, percentage purity you can calculate by m by 2 into 100. So that will be a percentage purity of your oxalate sample. Very simple question, but now I'll be moving to a little more easier. Then we will discuss this question. 150 ml of I2 is divided into two unequal parts. Hyposolution in acidic medium. Like first part is added to hyposolution acidic medium. 0.4 molar 15 ml hypo is consumed. Second solution is added to 100 ml of 0.3 NaOH, and base requirement, like the residual base that required are 10 ml of 0.3 molar H2SO4. So we don't need to consider V part 1, part 2. We can just directly do it. See, here, if you balance the equation, we know that I2 gives 2I minus, S2O3 gives S4O6. 6 moles of S2O3 is consumed, so 3 millimoles of I2 is consumed. So now over here, if you balance the second part reaction also, second part says that NaOH is added, and the previous question we had seen that I2 plus OH gives disproportionation, so I minus and IO3 minus. Then remaining base is 6 moles, 6 millimoles. So 30 minus 6 moles of OH is used in reaction. So see, basically here they had given that required a 10 ml of 0.3 H2SO4. So number of millimoles of H2SO4 is equal to the number of millimoles of base that is used up, that is left behind. So that is 3 into 10 into 0.3 into 10 into 2, which is 6, right? So that's why I got 6 millimoles. So from here we can conclude that 30 minus 6, whatever is originally there, um, minus the excess is used in the reaction. So obviously from the stoichiometric ratios, we can see that 6 moles of OH uh, are being used for 3 moles of I2. So obviously 24 moles of OH can be used for 12 moles of I2. So then total number of moles of I2 is 12 plus 3 from here, from part 1 and part 2. So we got 15 moles of I2, and then total volume is 150. So we can get the answer to be looking at like 0.1. So that is our answer.